Now that you've learned direct and inverse variation, we're going to go ahead and take the idea of inverse variation a little bit farther. So if you remember, inverse variation was y equals k over x. Now, we use the form y equals k over x because most of the time we use y to represent a function. And so if we rewrite that, you can see we have the function notation f of x equals a over x. And so we basically replace k with the value a. Now, that creates a function. And if you keep in mind, if you remember, the a value in all of our other functions always kind of represented a multiple that either stretched, that either stretched or compressed the given function. And so we'll see how that looks in a little bit. Now, the main parent function that these all stem from is what we call the reciprocal function. And so we have 1 over x, and so 1 being the smallest value for a over x. And so you can look down here in the key concept box and get a general idea of what that graph would look like. Now, if you notice, as the graph, the red curve, gets closer and closer to the x-axis, it starts to kind of tend to get closer and closer but never cross or intersect. That is called an asymptote, and we reviewed asymptotes in the first semester. And so if you remember, the asymptote kind of acts like a barrier. Now, sometimes the graph will cross the asymptote. So basically what the asymptote is doing is it's dictating in behavior on the x-axis, and it's actually creating a barrier on the y-axis. And so we'll talk about that in more detail as we go into the next lesson. Now, if you also look at the key concept box, you can see the a, the h, and the k, and we can still do the same transformations to this function that we've been able to do to every other function so far. So this is just a quick little introduction to reciprocal function and how it stems from inverse function, or the inverse variation, excuse me. In the next video we will go over some sample problems.